Hello, this is David Devney. I am hoping to fulfill the video portion of the final. So as you can see, I'm just filming from my phone. I'm gonna upload it to YouTube in a minute here. So have everything handwritten. Mission 1 was to secure the barricades. It's basically the hash table hash function. And then so we used the division method because it's a K mod M, which is basically K over M, and then whatever the remainder would be the value that we're concerned with. So there's 7 keys to insert, and they're right there. Collisions. So I right here, I used separate chaining, and I chose that because it was the first thing I thought of, and it basically all the slots have a pointer to a linked list. Even if it's empty, it doesn't matter, it still exists somehow. And so like in slot 1, actually I need to update that too, because that needs to go 17. It needs to be added on to 3. I'm gonna do that real quick. Okay, so right there. Actually, I did that wrong. Okay, cool. So yeah, so like in slot 3, there's 3 of them. So I just go to the end of the linked list. It kind of increases the time complexity, but it would only make it go from O of N, or make it go from O of 1 to O of N, I believe. And so 3 alternative methods would be, one would be linear probing, quadratic probing, and double hashing. I meant to write hashing there. So the first one is just it's kind of like picking a spot, and if the spot's not open, you look to the next spot. And quadratic is just the same thing, except you're kind of manipulating what the spot number is. And double hashing, you got 2 hash functions, and you do it from that. And then okay, gotta hurry up. Mission 2, build escape routes. So these are all your locations. My task: find a minimum spanning tree to escape. Show all the routes selected in order. Compute total danger level, and that'll be the time to escape. Right here. I'm gonna sort the edges by the danger level, which equates to the weight. And then step 2. So basically, after everything's said and done, the little check marks, those are my 5 guys. So first one, second one, the 4th one, and the 6th one. And as you can see, the other ones got rejected because they form a cycle and one cycle. So the minimum spanning tree includes those, like I said, and then you just basically add those weights. So you got 1 plus 2 plus 4 plus 6 gives you 13. And that was it. And mission 3, and craft a weapon. So that's the rod cutting. So we got a rod length of 8, got some prices there. Gonna fill in the dynamic programming table, which so max revenue, strongest arsenal. So each correct, blah, blah, blah. Okay, so the maximum revenue after everything's said and done is $22, and that's with 2 cuts, and that's at the 2 foot, or yeah, at 2 and the 6. And in dollar means wise, that's $5 and $17, totaling $22. Mission 4. Alright, so double decode zombie signals. So we got zombie attack, safe zone, David. Alright, so we're gonna kind of initialize things, kind of say X is signal 1, Y signal 2. Got this right here, and so the way that I figured this was the first time going from the upper left corner, first time that 2 letters meet each other, I would put a 1, and then the reason that E after the F in safe and the E in zombie doesn't trigger 2 is because its upper corner is 0, so it's 0 plus 1, and so it's still 1. But then when you get to the O over here, it's got the 1 in the upper corner, so that's why it's 2. And that's significant because that's where this thing switches. Same thing with the 3 and the 4. And those are my 4 letters. So I got a length of 4, ZOEA. Alright, mission 5. Park supplies. Alright, fractional knapsack. We got all this. We're gonna just sort it by ratio. And it goes like that, looks like that, looks like that. And then basically the first 3 items can fit fully. And then the 6th item, we're gonna get a fraction of that, so it's like 40 over 60, which is 2/3 basically of 200, to give you that, roughly 133.33. And then compute the max value, 60 plus 100 plus 120 plus 133.33 equals 413.33. That's it for mission 5. Mission 6. Okay, so we got these vertices. We're going to do the Bellman Ford. We got these vertices. We got these edges, these weights. I just abbreviated everything because it's easier. So starting level was the previous number divided by 10, which gives you 41.33. And so right here, we're going to start with the vertices. We're going to initialize distance 41.33 for AH, and then parents nil for everything else, and then the little infinity sign for everything else, just to initialize, meaning that we haven't discovered it, but it could exist or whatever. Alright, so iteration 1. That's a whole bunch of stuff right there. That's basically the first, we're going to start from AH, so it says, and I'm going to go to the first 2 possible vertices. We got distance 41.33, weight is 6, and then so that's going to add 6. So we get that 47.33, and then that's significant important only when it starts at PB, and then you notice it goes. That's where that 47.33 goes. If you follow that all the way through, I mean, it's kind of the same, thought process. Distances after iteration 1, so we got that. After iteration 2, basically found the shortest route, which is 39.33. And then, so Bellman Ford is designed to find the shortest path in the total amount of edges minus 1 iterations or rounds. So in my case, it's 4. But to check for negative cycles, you can run a 5th round in my case, even though 4 was necessary to find the shortest path. And then so in doing so, if there's any locations that can still be reduced, well, that is only because a negative cycle can exist. So the danger is a negative cycle could mean looping forever to decrease the distance, and nobody wants that. So in my specific task, in the 5th round, no locations needed to be needed to be reduced, signaling no negative cycles. And this concludes my final. Thank you for listening. Have a good day.